So we'll now have a look at the second part of this topic. So the first part was obviously uniform circular motion. The second part of this topic is gravitation. So we'll cover the basics in this lesson, and then next week go on to look at how this is applied to satellite motion. So what we're looking at here is the work of Isaac Newton, or some of his work in the 1660s. So he was interested in gravity and how it worked. The story goes that he saw an apple or it fell on his head and that made him think of gravity. Well, that's not true, but he was very interested in trying to explain how a force like gravity can attract objects without being in direct contact with those objects. So how is the moon attracted towards the Earth if there's nothing between the moon and the Earth? What carries the force? Now, he wasn't able to actually answer that question himself. It wasn't until later, when Michael Faraday introduced the concept of a field, that we were able to do this, but he did formulate his law of universal gravitation, which expressed in words sounds a little bit like this. Any pair of massive bodies, that means objects that have mass, will attract each other with a force whose magnitude is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. And this force will always be attractive and will always act along a line joining the center of these two masses. So essentially what that means is any object that has mass will attract any other object with mass through a force of gravity. Now, for objects like, a coffee cup or a human being, that force is extremely weak. But when we're talking about objects the size of planets, moons, asteroids, that kind of thing, it does become significant. And that force is always attractive. There's no such thing as a repulsive force of gravity. It would be like anti-gravity. It just doesn't exist. So how do we actually formulate this? Well, we normally express it like this. So you can see in this diagram we've got two masses m1 and m2 separated by a distance r, and the force of gravity, or the magnitude rather, can then be calculated using the formula shown in the bottom left corner, this one here. F equals g m1 m2 over r squared, where g is what's known as Newton's universal gravitational constant, which has a size of 6.67 times 10 to the negative 11, and that is universal. That is the same everywhere in the universe. You have to be careful here to differentiate that from little g, which we'll get to a bit later on, which is acceleration due to gravity, and that can be different in different parts of the universe. So acceleration due to gravity on the moon is different to acceleration due to gravity on Earth. So big G is the same everywhere in the universe. Little g, as we'll see later, can change. All right, and the next thing you need to know is that Newton's law is consistent. Newton's law of universal gravitation is consistent with Newton's third law, which means, well, Newton's third law says that for every action there's an equal and opposite reaction. In other words, if one object exerts a force on a second object, that second object will exert the same magnitude force back, but in the opposite direction. And we can kind of see that here in this diagram. M1 experiences a force of attraction F towards M2, acting along a line joining their centers. And M2 experiences the same force, but in the opposite direction. So you can see that M2 experiences a force F towards M1. So both masses experience the same force, same magnitude force, but in opposite directions. So Newton's law of universal gravitation agrees with Newton's third law, even though the force occurs between two bodies that aren't touching. So for example, if we're talking about the force of gravitational attraction between the Earth and the Moon, the force of gravity on the Moon is the same force of gravity acting on the Earth, but just in the opposite direction. Okay, so that's important. So moving on, a few examples here. So the first one we have here, we have two masses, two people rather, one with a mass of 80 kilograms and one with a mass of 65 kilograms, separated by a distance of 3 meters. So it's a pretty straightforward calculation. Just put your numbers in. The main source of error here, well, there'd be two main sources of error. Firstly, to forget to use SI units. Secondly, forgetting to square the r term down the bottom. So it's quite often you'll see people divide by r rather than dividing by r squared. Very important. Now you can see when we do that, we get an answer of 3.8 times 10 to the negative 8 newtons. And because it's a force, we need to include direction, so we can just say attraction. So it's quite small force. In fact, so in everyday life, you won't notice the force of gravitational attraction between two people because the force is tiny, and that force can be completely overwhelmed by the force of friction that makes it difficult to move objects, when they're standing on the ground. So the force of friction between your boots and the ground will be greater than this force of gravity, so you won't move. You'll never notice it. Where gravity does become significant is when you're starting to deal with large bodies. So for example here, find the force of gravitational attraction between the Sun and Jupiter, given the following astronomical data. So the mass of Jupiter, the mass of the Sun, and the mean radius of Jupiter's orbit. In other words, the distance between Jupiter and the Sun. We call it a mean radius because most planets move in a nearly circular orbit. Technically they're elliptical, but for most planets it's nearly circular. But it's not perfectly circular, so there will be some times when they're closer to the Sun and sometimes when they're further away. Some planets or things like comets have a completely elliptical orbit, Pluto for example. But the inner planets and even the gas giants like Jupiter and Saturn have a fairly circular orbit. Anyway, so moving on. So again, it's just a matter of taking those numbers, putting them into the formula, not forgetting to square the r² term down the bottom. But this time, when we look at the force, it's huge, 4.16 times 10 to the 23 newtons. So gravity is a strong force for objects of mass, like large mass, like planets, and insignificant for objects of air scale, everyday life, a couple of dozen to 100 kilos, insignificant, unnoticeable. Okay, so that's the basics. Now, the other thing we have to consider in this topic, and this will become also important later on when we look at things like Coulomb's law for electric force, which is very similar in structure to Newton's law, but obviously for electricity, is what we call proportionality. So proportionality enables us to work out how the size of a force will change if we increase or decrease one of the variables by a certain factor. And the reason proportionality is important is it allows us to quickly work out the new force without having to completely repeat that calculation. So if we think about what we have with the universal gravitation force formula, we have masses in there, so mass m1 and mass m2, and we also have the distance r between their centers. So we have to talk about how changing any one of those three affects the overall force. Now, when it comes to the masses, the force is directly proportional to those masses. So what that means is, if we double one of the masses, the force doubles. If we triple one of the masses, the force triples. If we half one of the masses, the force is halved also. So whatever change you make to the mass, you get the same change to the force, same size, so same factor change. If you were to change both masses at the same time, then the overall change to the force would be the product of those changes in the masses. So, for example, as we see here, if you were to double one of the masses, so make it 2 times bigger, and you triple one of the other masses, make it 3 times bigger, then the overall change in the force of gravitational attraction between them will be a factor of 2 times 3 equals 6. So in other words, if we make those two changes, the force of gravitational attraction will become 6 times larger. Or another example, if I halved one of the masses by quadrupled one of the other ones, so made it 4 times bigger, then the overall change there would be a half times 4 equals 2. So that the force would then get 2 times larger than it would be originally. So that's pretty straightforward. The harder one that people sometimes struggle to get their head around is the whole inverse square part. So when we say inverse, we mean that as the distance between the centers gets larger, the force gets weaker. It makes sense, doesn't it? Because you're moving the two masses further away. So that's what inversely means. As one goes up, the other goes down. But it's an inverse square, so it means we're dividing by r squared. Now, the effect of that's a little bit tricky to get your head around. So we've got a few examples here. Once you've seen a few of them, you can kind of get the pattern. All right, so if you double the separation, make it 2 times larger, then the force, as you can see here, decreases to 1 over 2 squared, remember it's r squared, 1 over 2 squared, which is 1/4 of its original value. If you triple the separation, if you make it 3 times bigger, then your force will decrease to 1 over 3 squared, or 1/9 of its original value. Picking up another one that's not shown there, if we quadrupled the separation, made it 4 times bigger, then the change in the force would be 1 over 4 squared, or 1/16 of its original value. All right, so that's what happens if you make the separation bigger. If you go the other way and you make the separation smaller, well, as you can see here, let's suppose we halve the separation, then the proportionality change here will be 1 over a half squared. So 1 over 1/4, and 1 over 1/4 is just 4. So if you halve the separation, you get 4 times the original force. If you make the separation 1/3 of what it originally was, then you'll get 1 over 1/3 squared, which is 1 over 9, or 9 times larger. And you can see here, if you make the separation 1/4 of its original value, then the force increases by a factor of 1 over 1/4 squared equals 1 over 1 over 16 equals 16 times larger. So that's the effect. Now, if we were to graph that, we end up with something like this example here. So what we have here is we have a little graph down the bottom that's showing the distance, and it's in units of d, which is the, I should have used r really, but it's the radius of the Earth. So you can see here we've got an apple, and that apple experiences a weight of 1 Newton. Now, remember, if we go back to our year 11 here, mass is measured in kilograms and is a scalar. Weight rather, when we talk about weight, we're actually talking about the force of gravity. So remember, your mass doesn't change regardless of where you go on the Earth. So if you have 75 kilograms of mass on Earth, you'll have 75 kilograms of mass on the Moon or on Jupiter or whatever. But if the weight's the force of gravity, well, actually, when you go to different parts of the universe, gravity changes and therefore the weight changes. So what we've got here is that on Earth's surface, this apple has a weight, in other words, a force of gravity acting on it, of 1 Newton. And what this graph shows us is how that weight would change as we go from 1d, so 1 times the radius of the Earth, to 2d, 3d, 4d, and so on. And you can see that particular shape, sort of like a, what would you call that? Well, it's an inverse quadratic. That particular curve is characteristic of an inverse square law. So you'll see the same curve when we get to do Coulomb's law later in the year. So you can see here the apple has a weight of 1 Newton on the Earth's surface at a distance of d from the center. Probably should mention here that, as the formula shows, that the gravitational attraction depends on the distance between centers. So basically, we can sort of treat gravity on Earth as though it's coming from the center of the Earth, because it's between the center of, say, the apple and the center of the Earth. That's the distance d. So when it's 1d away from the Earth's center, the apple has a mass of 1 Newton. If we go out to 2d, so twice the distance, then the change in proportionality will be 1/4 of the original force. So in other words, 1/4 of a Newton. If we go out to 3d, then it becomes 1/9 of the original weight, so 1/9 of a Newton. If you go out to 4d, it's 1/16 of a Newton. If we went out to 5d, it would be 1/25. If we went out to 6d, it would be 1/36, and so on. Okay, so that kind of illustrates it graphically. So that's proportionality. Proportionality, as we'll see in this example, is useful because you can solve this problem. This problem here has 4 parts to it. You can solve it by only having to do full calculations for the first part. So you use Newton's law of universal gravitation for the first part, and then you can just use proportionality to then solve B, C, and D, and that's a lot quicker. You could use Newton's law of universal gravitation for all parts, but that would be a waste of time. It's going to take you a lot longer to do that, and you have a high chance of making a mistake. So proportionality is much more sensible. So anyway, this example, we have 2 asteroids. One has a mass of 2 times 10 to the 18 kilograms, the other one has a mass of 3 times 10 to the 18 kilograms. And they're separated by a distance of 4 million kilometers, or 4 times 10 to the power of 6 meters. Sorry, 4 million kilometers, 4,000 kilometers. So what we want to do here is use proportionality to find A, the force of gravitational attraction between them at their original separation, B, the force of gravitational attraction when the mass of the first asteroid is tripled, so that's this guy, probably should have labeled him a bit better, and then C, the force when the mass of the first asteroid is doubled and the mass of the second asteroid is halved. Then lastly, the force when their separation is quadrupled. So each of these is like a different part. So let's have a look at the first part. Well, for the first part, we have to have to use the formula, right? So we just stick the numbers into the formula, and we get an attraction force of 2.5 times 10 to the power of 13 newtons. So that's like, for each of the subsequent parts, that's our original force that we then modify using proportionality. So if we go on to part B, so 2.5 times 10 to the 13 is our answer to part A. If we go on to part B, we're saying we're tripling the mass of the first asteroid. So if you triple the mass of the first asteroid, then because the force is directly proportional to the mass, that means the force will be tripled as well. So all we have to do is take the answer from the first part, which is 2.5 times 10 to the power of 13, and do what I've done here. Just times it by 3. So 2.5 times 3 is 7.5. So we just get a force for the part B of 7.5 times 10 to the power of 13. Easy. Part C, going back to the original answer now, so 2.5 times 10 to the power of 13. What happens if we double the first mass but halve the second? Well, doubling the first mass would double the force, but halving the second mass would halve the force. So if we put those two changes together, 2 times a half, 2 for the first change, half for the second change, that just equals 1, right? So basically in this case, the two changes sort of cancel each other out, and the magnitude and the direction of the force remain the same. So that's pretty easy too. Again, simple calculations to do, not hard. And then part D, what suppose we took that original answer of 2.5 times 10 to the 13 newtons and quadrupled the separation, made it 4 times larger. Well, if we do that, the reduction in force will be 1 over 4 squared, or 1/16 of its original value. So it's just a matter of taking the original value, 2.5 times 10 to the power of 13, and dividing it by 16. And when we do that, we get a new attractive force of 1.6 times 10 to the 12 newtons. So you can see in this example here that you could have used Newton's equation for all 4 parts and still got the same answer, but it's much easier to just do the full working out for the first part and then use proportionality of the following 3 parts. And if you get a question in the test, do it that way. Alright, so that's proportionality. Last bit for this, this little video lesson is calculating acceleration due to gravity. Now, we know that on Earth, acceleration due to gravity is 9.8 meters per second squared, but we've never shown why. So now we have the apparatus to be able to do it, because we know how to calculate the force of gravity between 2 objects. And we can modify this formula to find acceleration due to gravity, little g, right? So it just works like this. You start with your universal gravitation formula, and then over this side, well, we know that F equals ma from Newton's second law. So what I've done over here is I've just replaced F with ma, but instead of ma, I've put m little g, because remember, little g is the special symbol for acceleration due to gravity. So I've just got mg equals g m. Now, what I've done over here is we're talking about acceleration due to gravity on a body like the Earth, right? So little m represents the mass of the object that's on the Earth, like, say, an apple, for example, going back to that previous slide. Whereas capital M is usually reserved for the mass of the central body itself. So if it's an apple on Earth, M would be the mass of the Earth. If it was an apple on Jupiter, M would be the mass of Jupiter. So we're using different capitalizations there to distinguish between the two. So you can see here, obviously, that there's a common factor there. The mass of the object we're interested in, the apple, say, appears on both sides, so we can just cancel out the 2 little m's, and we end up with this formula here. Acceleration due to gravity, little g, equals big G times big M divided by r squared. So it's very similar to the universal gravitational formula. So how is it applied? Well, let's have a look at an example. Let's just show that acceleration due to gravity on the Earth is 9.8 meters per second squared. But to do that, you need this information here, which is when you have a test or an exam, it will be given to you on the SACE formula sheet. I can't remember if they're exactly the same, to the exact same number of significant figures, but it's the same basic number. So we've got the mass of the Earth, and we've got the Earth's radius at the equator. In other words, the mean radius of the Earth. When we say mean radius of the Earth, well, the Earth is not actually a perfect sphere. It's what we call an oblate spheroid. Basically, as the Earth, because the Earth is not completely solid, it's got molten liquid inside, so it's kind of a little bit squishy on the inside. As it rotates, it's moving fairly quickly, particularly at the equator. It doesn't move as quickly as at the poles, but at the equator, the actual molten stuff underneath the Earth is moving fairly rapidly. And that movement tends to make the Earth bulge out. So imagine you took like a sphere, a jelly sphere or something like that, and spun that jelly sphere really fast. You can imagine it bulging out at the edges and eventually falling apart. And that's kind of what's happening here. We're kind of getting a little bit of bulging out. Sorry, I said edges, didn't I? Bulging out at the middle and kind of a pinching in at the poles. So you can see here that at the equator, the diameter of the Earth is 12,756. But if you go the diameter across the pole, so from the North Pole to the South Pole, you get 12,714. So basically, when you're at the North Pole, you're a little bit closer to the center of the Earth, and therefore gravity is a bit stronger. When you're at the equator, you're further away from the center of the Earth, and gravity is weaker. Not by much. It's a very small difference in comparison to the difference in diameters is tiny in comparison to the actual diameter size itself. So it's not a noticeable difference, but that's what we mean when we say the mean radius, because the Earth is not a perfect sphere, so you'll get different values for the radius if you measure at different points. Anyway, so what we do, it's pretty simple. We just take that mass and take that radius, throw it into the formula we had from the previous page, G, like big G, big M over R squared, which is what I've done here, and crunch the numbers. And when you do that, you do indeed get 9.8 meters per second squared. So that would be like the average value of acceleration due to gravity. Obviously, when you're further away from the center of the Earth, it'll be larger. When you're closer to the center of the Earth, it'll be smaller, right? So it's kind of like an average value, just because we used the average radius, didn't we? So that shows that the acceleration due to gravity is 9.8. If we move on, look at a few more examples. What suppose we were interested in what acceleration due to gravity was on the top of Mount Everest? Because, you know, when we're up there, we're further away from the center of the Earth, so therefore it should be weaker. And then from there, part B, we'll have a look at what happens if you're on the International Space Station, which is 340 kilometers above the Earth's surface. Should be even weaker still. So for part A, the acceleration due to gravity on Mount Everest, well, to find the distance between the center of the Earth and Mount Everest, because that's our R value, we need to take the mean radius of the Earth from the previous part, 6.378 times 10 to the power of 6, and add on the height of Mount Everest in meters. That's important there, in meters. When we get that R value, then just take it, insert it into that same equation, and you can see here when you do the working out, you get 9.773 meters per second squared to 3 decimal places. So it's like a little bit weaker on top of Mount Everest, but not noticeably so. You know, if you dropped a ball on top of Mount Everest and you dropped a ball at sea level on Earth, they'd hit the ground at pretty much exactly the same time. You wouldn't be able to notice the difference in times. It'd be slightly longer to hit the ground on top of Mount Everest because gravity is slightly weaker, but not so you'd ever notice. But what if we went up to the International Space Station instead? So now, for part B, we have to add on 340 kilometers to the mean radius of the Earth. So we get this 340,000, because remember, it has to be in meters, plus 6.378 times 10 to the power of 6 gives you the radius, and then take that radius and plug it into this equation. And you'll notice when you get that, the acceleration due to gravity is 8.833 meters per second squared. So less than it is on Earth, but not significantly less. And this is where it gets interesting, because we see people up on the International Space Station, and they're floating around in, in inverted commas, what we call zero gravity. So a common misconception is once you get into space, gravity disappears, right? But in fact, as we can see from this calculation, gravity is still fairly significant, 340 k's above the Earth's surface in space. Gravity can't disappear because there needs to be a force of gravity holding the moon in orbit around the Earth. So if gravity just disappeared once you got above the Earth's atmosphere, every satellite we send up there, the moon itself would just fly off and never come back. So gravity is still fairly significant up there. So what's happening there, and we'll look at this later in the topic, is zero gravity is not because there's no gravitational force. It's basically an illusion because objects in satellite orbit are actually free-falling around the Earth in a circular path. We'll talk about that later. So essentially what it's saying here is if you could somehow build a platform 340 k's above the Earth and climb up onto some huge ladder up to there, when you stood on top of that platform, you would feel lighter than you do on Earth, but not significantly less. And the only reason we feel weightless in the space station is because of that free fall sensation. But we'll look at that in more detail later. Okay, and then one last example. So let's suppose we were to go to a different planet or a different celestial body and work out acceleration due to gravity there. And you can do it for anything. For example, on the moon, the force of gravity is like 1/6 of what it is on Earth. So instead of being 9.8, it's 9.8 divided by 6, which I can't remember what that is. Let's have a look. 1.6. So it's 1.6 meters per second squared, so 6 times weaker, and therefore you can jump 6 times higher on the moon. But let's suppose we decide to look at Mars. So if you get questions like this in tests or exams, well, the mass of the Earth and the radius of the Earth are given to you on the SACE formula sheet. But anything else will be given to you in the question. We don't expect you to memorize the mass of the Sun or anything like that. So here, on the surface of Mars, it has a mean radius of 3.396 times 10 to the power of 6 meters, and a mass of 6.419 times 10 to the 23. So what's acceleration due to gravity on Mars? Well, plug in the numbers, and on Mars we get 3.7, so about just under 3 times smaller than on Earth. So you could jump about 3 times higher on Mars. So you can see we can apply this to anything. We could do it for something like the Sun, and we would find an acceleration due to gravity on the surface, in inverted commas, of the Sun is higher than it is on the Earth. So you can do it for different bodies. But anyway, I think that'll do us for now. When you come back to school next week, we're going to move on from this. We'll do some SHE stuff as well, but we'll move on from this to look at the last part, which is on what we call Kepler's laws of planetary and satellite motion, and the actual sort of theory of how satellites work themselves, and have a bit of a look at the different kinds of satellites we put up into orbit. All right, so make sure you respond to the questions that go with this. Make sure you do the homework questions I'm going to set on DayMap, and we'll see you next week.